There's no such thing as one single plastic. Different types of plastic have different chemical structures, different behaviors in seawater, and most importantly, they require different microbes and different enzymes to be broken down. Take Ideonella sakaiensis, the bacteria we covered earlier. It can digest PET, the plastic used in water bottles and polyester fabrics, but give it polyethylene or polypropylene, it does nothing. So if we want to evaluate the role of microbes in cleaning up marine plastic, we can't treat plastic as a monolith. Here's what plastic really is. It's a polymer, which means it's made of very long chains of repeating molecules called monomers. You can think of it like a pearl necklace, where each bead is a small organic molecule. The necklace can be hundreds or thousands of beads long. Now here's the key part. These chains are tough. They don't dissolve easily in water. They're built to be stable, durable, and inert, which is great for making packaging, but terrible for the environment. For microbes, breaking down plastic means doing two things: attaching to the plastic surface and severing the chemical bonds between monomers, one link at a time. And that takes very specific enzymes, biological scissors adapted to one particular type of chain. That's why each plastic type requires a different biodegradation pathway. Some polymers, like PET, are more susceptible because their bonds are easier to hydrolyze. Others, like polyethylene, have stronger carbon-carbon backbones and are much harder to break. So when we ask, can this microbe eat plastic? The real question is, can it recognize the chain, attach to it, and cut it apart efficiently? Now let's look at what plastics we actually find in the oceans. Polyethylene, PE, is by far the most common. It exists in high density and low density forms, HDPE and LDPE. Together they represent 40 to 50% of marine plastic waste, used in bags, films, bottles, containers, nets. It's chemically simple, just carbon and hydrogen, but that simplicity makes it extremely resistant to biodegradation. Next, polypropylene, PP, about 20 to 30%. It's found in caps, straws, ropes, food boxes, and floats easily. But it's also chemically tough. Between PE and PP, we already cover 3/4 of all ocean plastic. PET, polyethylene terephthalate, is next at around 5 to 10%. It sinks rather than floats. You'll find it in drink bottles and textile fibers. It's more complex chemically, but also more vulnerable, which is why it was the first to be partially digested by a known bacteria. But that bacteria came from a landfill. It doesn't survive in salt water. Polystyrene, PS, including its foam version, represents about 5 to 10% too. Used in trays, packaging, insulation, it breaks easily, releases toxic residues like styrene, and spreads as microplastics. PVC, polyvinyl chloride, is only about 5%, but it's especially problematic. Used in construction, pipes, and cables, it contains chlorine and releases toxic byproducts when it degrades. Phthalates, dioxins. It's not the most common, but it's one of the most harmful. And finally, there's a group of miscellaneous plastics: nylon, polyurethane, acrylics, ABS. These account for 5 to 10% of the total. They come from textiles, fishing gear, foams, and technical parts. They're diverse, and so are their degradation mechanisms. We won't break them down here. Just know they exist. What about biodegradable plastics like PLA or PHA? They were designed to break down more easily because, unlike conventional plastics made from petroleum, they're built from natural building blocks like starch, lactic acid, or plant sugars. That makes them more accessible to microbes. We'll look at what really happens to them in a future episode. So what does this all mean? It means that the plastic floating or sinking in the sea isn't one single material. It's a chemical cocktail of polymers, each with different properties and different resistance levels. If we want microbes or enzymes to help us, we'll need a diversified toolkit because no single organism can break it all. Next time, we'll look at what biology has come up with so far.